What's up, students? Mr. Harrison here from school. Here is your applications of interaction and interactions of sound waves slideshow. There's a few videos embedded. I'll prompt you to pause this video to open the links that will also be shared with you separately, and then re-engage the video when you're done. So let's get started. The first application sound waves is called resonance. I'll say it again, resonance. It comes from the word resound. They both come from the same root word, resonance. It's a process by which an object is made to vibrate by absorbing energy at its natural frequencies. And this can cause the objects to absorb more and more energy if you continue this. So every object in existence has a natural frequency that if it's struck, it will vibrate at that frequency. And remember, when we're talking about sound waves, frequency and pitch are the same thing. So when we're talking about the frequency of a wave, that correlates to what we perceive as pitch. So as I said, it can be used to make an object absorb more and more energy, and it serves to practically magnify the wave and drastically increase the object's vibration. So if you follow that even further and you continue the wave into an object, causing it to vibrate at its natural frequency more and more and more and more and more, magnifying the wave, it can even cause the object to break apart. And this is how it is, in fact, truly possible to break a glass by singing into it or by playing a single note continuously. It's also thought to be responsible for the Tacoma Narrows bridge collapse. Technically, it's not resonance. It's something very similar. But for the purposes of the Virginia State Standards, they consider it resonance. So here are your two famous examples of resonance. So I'm going to pause here and give you a chance to click first the singing wine glass, which is the top video with yours truly in it. And then once you're done with that, immediately go to the breaking a glass with your voice. So pause this video, click on first the resonance video, and then the wine glass resonance slow motion video. Go ahead and do that and then unpause the video. All right, welcome back. Hopefully you just watched these two videos. There will be questions at the end, so make sure that you have access to these if you need to rewatch them later. And the second famous resonance application is from the Tacoma Narrows bridge collapse. So now at this point, please pause the video you're watching and cue on the Tacoma Narrows bridge collapse video, and then unpause this original video when you are done. Go ahead and do that. All right, welcome back. We're going to move past resonance now. Remember, it's resonance that causes the wine glass to vibrate and then break if you continue it. And it's resonance that's responsible for the Tacoma Narrows bridge collapse. Resonance. All right, this one I'm going to breeze through because it used to be required by the state of Virginia, and then they changed their standards, but it's still really cool, I think. So I'm just going to talk about it just for a second. The Doppler effect. You might have heard of this in terms of Doppler radar for weather. The Doppler effect is a phenomenon of sound because sound is a mechanical wave and it must move particles, namely the particles of gases in the atmosphere. And when it moves that medium, because it's a physical medium that's moving, if the sound source or the sound observer is moving, then you can manipulate the sound by like the motion of either the source or the recipient of the sound. So remember, frequency is pitch. So low frequency, high frequency. And when you have a source of sound that's moving towards you, it's moving towards you from farther away, getting closer, it actually will serve to squish the wave even more because it's moving towards you. So according to your ear, all the air in the atmosphere and the gases in the atmosphere get squished even more than normal. So as an object approaches you, it actually appears to your ear to sound higher pitch. And then once it passes you and goes farther away from you, it actually serves to stretch out the sound wave so it appears to go lower pitch. If any of you have been to a racetrack, you've seen this in action because race cars, as they approach you, seem to be higher pitch. And when they go away from you, they seem to be lower pitch. And in fact, to your ear, they literally are. It literally does change the frequency to your ear, but not the actual frequency of the wave itself in isolation. So that's the part whereas as a race car approaches and passes you, you get something that sort of sounds like higher pitch when it approaches you, lower pitch as it goes past you. I'm sure you probably heard that, something like that. You can hear it with cars on the street as well. Movies portray that, but it's a kind of a cool effect of the pitch and frequency as you have a moving sound source or a moving sound recipient. All right. Some of this is review, some of it's not, but we're just going to keep moving on. Reflection. Reflection is probably what you're thinking about. It's the bounce back of sound waves. And that occurs when a wave strikes an object in its path and bounces off of it. So think like an echo. It can be useful in things like sonar, which is what ships use under the water to detect other objects. It also is used by animals through echolocation. Echolocation. And echolocation, many bats use this. Dolphins use this. Whales use this. There's even a few a very small amount of birds that don't see very well that use this in part as well. But the main three that use this on a regular basis is dolphins, whales, and bats. And that's where they emit a sound, and then that sound bounces back off of objects, and they get like an image of what is right in front of them, what they're seeing. And I apologize, there's a little beeping of a stopwatch going on, so try to ignore that if you can hear it. I don't know if the mic is picking it up. There's this thing called the law of reflection as well, and that says that the angle of incidence is equal to the angle of reflection. And if you've ever played pool or billiards or 8-ball, you've seen this in action. It's basically saying that the angle that a wave or an object goes into another object is going to be equal to the angle that it bounces off relative to a perfect perpendicular, like straight back bounce. And that's called normal. The angle where it bounces straight back is called normal when it's perpendicular. And the angle relative to normal as it goes into the wall or into the object, which is called incidence, is going to be equal to the angle relative to normal on the other side that it bounces away. That's all that's basically saying. Then you got reflection as the first one. The second one is refraction, and this is a form of transmission. Remember that light can pass through objects. Refraction is the bending of a wave caused by a change in its speed as it moves from one medium to another, because waves, light waves, sound waves, all waves travel at different speeds through different mediums. They travel different speeds through a solid than they do through a liquid, and different speeds through a liquid than they do through a gas. And so as a wave transfers itself from one medium to the next, it's going to cause the wave speed to change because it's a different medium it's traveling through, and that's called refraction. And then lastly, we've got diffraction, which occurs when an object causes a wave to change direction and bend around it. And this works because the sound waves travel at different speeds through different phases of matter. It's the same thing that kind of causes it, but in diffraction, instead of going through it, it's bouncing around it. And part of diffraction, and if you combine reflection, mostly reflection, but combine the principles of diffraction, that's how we're able to make an image out of like a sonar under the water emission of sound. It's also how whales, dolphins, and bats can determine what it is that's reflecting the sound, is because of the principles of diffraction. That's when a wave goes around an object in its path. So we've already talked about it a little bit, but echolocation is the process of locating objects by emitting sounds and interpreting the sound waves that are reflected back. Reflected. And bats do this to navigate at night. Whales do this. Dolphins do this. And as I said, occasionally a very small amount of types of birds can do this as well. And there's also a rodent, I believe, that does this somewhat as well. But bats, dolphins, and whales are the big three. Then you got sonar, which is a system that uses reflection of underwater sound waves to detect objects. Boats use this a lot. And then you have ultrasound or ultrasonic technology. And this is when high frequency ultrasound, that's why they call it ultrasound, is because it's very high frequency, high pitch. Ultrasound waves are reflected off a part of a person's body, producing an image much like the sonar in water, except in your body. This is made famous by the doctor visit for pregnant mothers who will be able to use ultrasonic technology to get an image of the baby even while it's still inside her womb. So it's a pretty cool, like to be able to see a human being before it's even born, to see an image is a pretty cool technology. And obviously this is relatively modern. Like people in the 1700s and 1800s weren't doing this. But that's how if you ever had the privilege of being on a visit with your mother or with somebody that was going in there, maybe a little brother or little sister was in the womb, and they rub like a gel on the belly, and then they put this device that emits a very high frequency that we can't hear, ultrasonic wave into that belly, and it reflects off of the baby inside, the human inside, and causes an image to appear. All right, at this point, close the video down and start answering the questions and move on.